Now this second one is rather interesting because it allows us to have a look at the well-known strong similarity between the sine and the cosine functions from two different perspectives. Well, let us just consider the only fact, or it's not really the only fact, but the basic fact that we want to use here is the fact that the first derivative of the sine of x function equals the cosine of x function. Looking at these very rough sketches here, the orange one should be the sine of x, the blue one the cosine of x. Generally, what you see is that they are almost identical, except for horizontal displacement. Now that's what we will use also, but you can, with blank eye, you can see that you could say the slopes of the tangents which we would construct at the orange curve are given by the values of the blue curve, right? So that, for example, where the sine of x crosses the origin with a slope of 1, by the way, the cosine exactly gives you 1 as a value. So the value of cosine is the slope of the sine, right? And at the maximum of the sine here at pi half, where the function value gets to be 1, well, say xy, yeah. There you see that blue curve crosses the x-axis. It meets the x-axis because this is to say that the slope of the sine of x tangent will be 0 at this position. So that's sort of a nice interplay between sine and cosine. So that's fact. Now we want to determine the first derivative of cosine of x, which we call to be g of x, right? But not by using the general method of, you know, sort of a difference ratio and the limit procedure to get a differential ratio, differential quotient, whatever. No, but instead we want to utilize the horizontal displacement between the graphs of these two functions. F of x should be sine of x, g of x should be cosine of x. And do so algebraically. Let's start. We use the fact that sine of x prime equals cosine of x. Now, we know that cosine of x may easily be expressed by using a sine function if we just insert a horizontal displacement. And please remember, if I say x plus pi over 2 here in the argument, this always means that I perform a left shift. This is always, again and again, this is a matter of confusion sometimes, okay? Why is it? Well, actually it's quite easy. If I add pi half to x, the resulting graph will be shifted to the left. So I transform the orange one to the blue one if you want, right? In this way. Check it out for yourselves. For example, you could check it by setting x equal to 0. So you get sine of pi half, which is 1, well-known fact, right? And actually the cosine of 0 equals 1. So everything's fine. That's you could say that's the displacement notation between cosine and sine. Now, what then might the first derivative of the cosine of x be like? What do we get? Well, cosine of x prime then equals, now look here, we can use the chain rule again. We have to take the outer derivative. So sine of x must be differentiated for x, which gets us cosine, but not sine of x, but sine of something equals then differentiated, it equals cosine of something. I just take this over, x plus pi half, right? Then I have to multiply the inner derivative. Now this time, this inner argument is so simple that its inner derivative is simply plain 1, right? Because differentiating this, you get 1 and the constant plus pi half gets away. The reason is simple. This is not even a linear scaling of our argument. it's just a horizontal shift, which never has, in a sense, it never has an influence on the rate of change of the variable x, right? Just shifting it to the right or to the left doesn't change its, it doesn't influence its rate of change. Just a second, please. Okay, what was I saying? I've got my focus. Well, yeah, it's just that the fact that we do not really need the inner derivative because it's 1. There is no effect on what we're doing here. So in the end, it was simple. We found out that, where am I? Yeah, due to this transformation, the derivative of the cosine function is again sort of a cosine function, but with a horizontal displacement. And now you could say, what we do is we apply this connection between cosine and sine again by saying that this modified cosine can one more time be expressed to be a sine function with a certain horizontal displacement. And since the displacement is always due to taking plus pi over 2, expressing a cosine using a sine, right? So inside here, this argument must be incremented by pi over 2 again. And so we get a sine function with an argument of x plus p, x plus pi, sorry. So this is x plus pi half plus another pi half, which is x plus pi. So that's relatively easy, actually. But now we recognize that in the end, this means we have shifted our sine curve not only by a quarter of a period here, but even by half its period. And as you all know, this is some also call it, let's say opposite phase. You know what I mean? Shifting such a periodic function by half its period, and by the way, it's a perfect alternating signal, where now this time the positive half wave gets replaced by the negative half wave, and the other way around, means that in the end what we get is the same thing as just the negative sine of x. So that's, well, some geometric considerations behind. Look at this. It's roughly the situation shifting by half a period. You get sort of a vertical, vertical reflection on the x-axis. So we call it opposite phase. In the end, it's a negative sine of x. And you can also, by inspecting this graph again, you can easily see that the slopes of the cosine curve of its tangents are given by the values of the sine function, but with the opposite sign. So with the opposite signature, right? So it means that cosine of x prime equals negative sine of x. This was one step, and this was one method to prove it. The other one asked here is, again, confirming, now this time confirming the result of part 1, but now using a different method, which is even nicer, you could say. It's using the unit circle equation, which we all know to be like that the squared sum of cosine and sine of x is always equal to 1. So this is one of the nicest equations of geometry, actually. And then, well, describing the whole geometry of the unit circle. That's what it means. That's what it contains. And now, of course, this is also very easy to be used in order to express a certain cosine, to transform it to be an expression just using the sine function. Okay, so this is different, but it hopefully gets us to the same result. Look at the unit circle equation again. Let us just isolate cosine of x. What do we do? Well, we subtract sine squared of x. And then in the next step, we take the square root, but carefully by considering the fact that cosine of x may be positive or negative. So we have to take into account the positive as well as the negative square root of this expression 1 minus sine squared of x. You see, this is the full and correct transformation of this equation in order to isolate cosine of x. Remember, cosine of x can also be negative, and in this case we have to use the minus sign. In the other cases we have to use the plus sign. So this is sort of a twofold split up version of solving the problem. Let's just try and do so by taking the derivative of cosine of x again. Well, we find that this is a root expression, so just disregarding the plus or minus or just taking it over, we know that here, you see it, the derivative of the root function is always 1 over 2 times square root of its argument. And if it's not square root of x, we just take this over. So we get 1 over 2 times the square root of 1 minus sine squared of x here, right? And as I said, taking over the plus or minus sign. So you could say that we simultaneously handle both cases, but then we must, of course, use the chain rule and multiply the inner derivative, where this time 1 gets away and negative sine squared of x, well, it has to be differentiated even using the product rule. No, sorry, the chain rule again. So we get negative 2 times sine of x power 1. You know what I'm doing? I'm using the power law, which says that x squared prime equals 2 times x, but now using whatever argument I have, my argument is the sine of x. So I'm using this one. And then I'm here where I say that I get minus 2 times sine of x, this one. And then I have to again, to differentiate the inner function, which is sine of x. So I have to multiply the inner derivative, which is derivative of sine of x equals cosine of x. So I have times cosine of x. Actually, that's it. Now I can cross out the factor of 2. I can, well, if I want, is it? Let me see. Yeah, that's interesting. Now getting rid of this plus or minus case distinction. The idea is to remember that this plus or minus square root expression was just sort of an auxiliary step in order to get things done. But now I can make the replacement. How do you say? Yeah, I can go back to the original expression, which is cosine of x. You see? So this plus or minus square root of 1 minus sine squared of x is replaced back to be, in both cases, to be cosine of x. So replacing this, I get cosine of x here, and still negative sine of x times cosine of x in the numerator. I can cross out cosine of x, and what remains is negative sine of x. So that was, well, hard again, but it's the same result. And even nicer, it's just for your info, is the following. It's, you should have heard it somewhere in school or in the lecture. It's possible to, well, to use the so-called implicit differentiation, which sometimes is applied simply to an equation. It's behind it, it's just the following thought behind. You have a valid equation. Now, since this equation is valid for all values of x, it means that this term, as complicated as it may be, is always equal to plane 1. And since this equation holds, it also holds that you can take the derivative on both sides, and it's still a valid equation. And that's what I'm doing. I'm taking the derivative of this expression here. Look what I'm doing. By the chain rule, I get 2 times the, due to the potency rule, 2 times cosine of x, but times inner derivative. Now, you see, since we want to find out what cosine of x prime may be or should be, we are not allowed to use the result from before, right? So at this point, I just say I need the derivative of cosine of x. So I just put cosine of x prime and say question mark because I still don't know it. This is just a thought experiment now, yeah. Now plus the next term differentiated, here I get 2 times sine of x, again due to the chain rule, times, and now I may use that the sine of x prime equals cosine of x, because again, also here I must multiply the inner derivative. And then the right-hand side, that's it. The right-hand side must also be differentiated, like symbolically by applying e over dx. You know, this is the classical notation for taking the derivative. Now, what is the derivative of 1, constantly 1, for x? And the answer is, of course, it's 0, because 1 is constant, it doesn't change. And so its derivative with respect to x equals 0. The whole expression must be 0. And now, first of all, I can cross out 2 times cosine of x, which appears here and here, just by dividing this equation, you see, by 2 and by this cosine of x. By the way, it should be unequal to 0. This is a little restriction which I make, which may be taken away afterwards, but let's not go too far ahead, considering details. Now, what remains is cosine of x prime plus sine of x is equal to 0 for all values of x. If I just isolate the cosine of x prime, get cosine of x prime equals negative sine of x in the next step. Okay, so that's just it's just another way of getting to this same result.